Last time, we saw the RNN's big weakness. As a sequence gets longer, the signal from an early event like malware drop to disk at step 1 fades almost to nothing by the time an alert fires 10 steps later. That fading memory problem is exactly what today's building block was invented to solve. What if, instead of relying on one compressed memory that degrades over time, the network could reach back and look directly at any earlier moment it needed, no matter how far away? Here's the core idea behind attention. At every step, instead of using just one fading memory, the network keeps around every earlier hidden state it has produced. Then it computes a relevance score between the current step and each of those earlier states, asking, essentially, how much does this past moment matter right now? The thickness of these connections shows that idea. Some past states end up mattering a lot, others barely at all, and the network decides that fresh every single step. Let's make this concrete with a security example. Picture a stream of log events. Step 1 is malware dropped to disk. Steps 2 through 7 are routine, unremarkable activity. Until step 8, where a suspicious outbound connection finally triggers an alert. With attention, the model doesn't have to carry that first event forward through steps of a fading hidden state. At step 8, it directly scores all the earlier events and can assign the highest relevance straight back to that original malware drop event, however far back it sits. To make this comparison concrete, attention frames it as a question and label matching problem. The current step forms a query, essentially a summary of what it's looking for right now. Every earlier hidden state carries a key, a short summary of what information that state actually offers. The network compares the query against each key to see how well they match, the same way you'd scan a row of luggage tags to find the one that matches what you're holding. Alongside its key, every earlier hidden state also carries a value, the actual content that gets pulled forward if that state turns out to be relevant. So the key is what gets compared against the query, and the value is what actually flows into the answer once a match is found. In our example, the log entry whose key best matches the current query, the malware drop event, is the one whose value contributes the most to what the model retrieves. Once every earlier state has a raw relevance score, the network needs to turn those scores into something it can actually use for weighting. That's the job of a function called Softmax. It takes the raw scores and converts them into a set of weights that are all positive and add up to exactly 100%. The state that scored highest ends up with the largest slice of that weight, but every earlier state still gets at least some small share. Now attention combines everything. It multiplies each earlier state's value by its softmax weight and adds all of those weighted values together into a single new vector called the context vector. Because the weights were driven by relevance, this context vector is naturally dominated by whichever past moments actually mattered, like our malware drop event, while irrelevant steps contribute almost nothing. It's a summary built fresh for this exact moment, not a single memory dragged along the whole way. Here's how this actually plugs into the RNN we already know. At each step, the RNN still keeps its own hidden state, but now it also computes this attention-built context vector by looking back across all earlier steps. The two are combined, and that combination is what actually feeds the prediction. The RNN hasn't disappeared here. It's still processing the sequence step by step. Attention is an add-on that gives it a direct line back to any earlier moment, patching its short memory problem without replacing how it works. So, to recap, attention lets a network score every earlier state's relevance, turn those scores into weights with softmax, and blend the matching values into a fresh context vector, giving it a direct line to any past moment instead of one fading memory. We first bolted this onto an RNN just to patch its weak memory, but researchers soon asked a bigger question. What if you built a whole architecture out of nothing but attention and dropped recurrence altogether? In the next video, we'll break down the transformer, the architecture behind GPT. So make sure you subscribe so you don't miss it.